Hi, I'm Travis Manderson, and along with my colleagues, I am pleased to present our work on self-supervised goal-conditioned policies for navigation in unstructured environments. The motivation behind our work is that we want to deploy robots in the natural environment for a number of tasks, including environmental monitoring or humanitarian crises, and we want to use small-scale robots because they scale well, their small size has limited impact on the environment, and they can perform in-situ measurements. However, there are a number of challenges, including reliability, endurance, and enabling navigation without a map, as well as traversing difficult terrain. For robots operating in rugged environments such as mountains or in the open ocean, there are a number of specific challenges they face. These robots must be able to infer traversable terrain, which is often made up of rocks, riverbeds, and slopes. Further, they need to be able to avoid obstacles such as trees, brush, large boulders, or coral reef. And the robot will need to reason about vegetation that is often traversable, like tall grass, but includes sensors such as cameras. And perhaps the biggest challenge is that the variety of terrain the robot will encounter may be unknown, so it will need to self-learn what it is and isn't able to traverse. There are several approaches researchers have examined for this problem. One method is imitation learning, where the expert demonstrates actions to navigate an environment, and these demonstrations are used to build a dataset of state and action pairs, which are then used to train a navigation policy. The main drawback to this approach is that it may not generalize across different environments without further demonstrations. Another approach is semantic segmentation, where the image is segmented based on similar appearing regions. These regions are then assigned a score based on their traversability sampled for each class. From this cost map, geometric path planning can be used to generate a feasible trajectory. One drawback to this approach is one risks over-segmenting the image, requiring the robot to sample many terrain classes. More recently, some self-supervised learning approaches have had success, which is the category our work falls into. At the very high level, in self-supervised learning, we learn a navigation policy that can predict a trajectory for the robot. The key idea is that as the robot executes a set of actions, it is able to measure its own performance and update the policy. So this can be repeated for a number of trials until the robot is able to navigate in a reasonable way. Now, in terms of reinforcement learning, these methods can either be classified as model-free or model-based, and each of these have their own advantages and disadvantages. And so in our system, we use a sample-efficient hybrid model that combines the advantages of each method. Our objective is to learn a policy for navigating natural, unstructured, and outdoor environments. To do this, we want to learn to avoid obstacles and navigate on smooth terrain and toward desirable regions. For an underwater robot, this might mean avoiding sandy regions and preferring to swim over coral for environmental observations. Finally, we want to reach a predefined set of geometric waypoints. A high-level overview of our system used for off-road driving is as follows. We start with an image taken on board the robot, which forms the observational state. The image is passed through a convolutional layer, which forms a hidden layer to the recurrent neural network. As the robot explores, it is able to measure its own performance in terms of traversability using an onboard IMU to measure roughness and LiDAR for collision. The navigation model learns to predict the probability of terrain class for a sequence of actions up to horizon length. And since we reward smooth terrains, we can sum the individual rewards to find the total for trajectory. At inference time, we sample a number of trajectories and choose the one that leads to the highest reward. We then execute the first action of the trajectory and repeat the optimization. Once we have trained the initial navigation policy, we make use of a technique called hindsight relabelling to treat previously visited states, as exemplified by the blue path, as intended goals. This allows us to train a waypoint condition policy offline from the data collected from the non-goal condition policy. Once we have a dataset of relative goals and the images and actions taken to get to the goal, we train a goal condition policy by combining the relative goal position with the initial hidden layer. Instead of training the model to predict the terrain class, we instead predict how close the input actions are to the observed actions conditioned on the image and goal input. We then take the action that has the lowest predicted difference. We validated our terrain predictive model in northern Canada on a 1/5 scale RC buggy, and used the RMS acceleration to measure the instantaneous roughness and LiDAR to detect collisions. We used this data to train the terrain prediction model and obtained good performance after 8,000 training steps. On the left are several examples of the trajectory predicted to move the robot towards or stay on the smooth terrain. On the right shows the detected smooth terrain in blue. We also trained the model in simulation using an Unreal Engine-based simulator. Using our terrain prediction policy, we reduced the rough terrain encountered from 42% to 11% when compared to a random policy, and increased the smooth terrain encountered from 33% to 80%. From the smooth terrain navigation policy, we trained a goal condition policy to navigate a sequence of waypoints. On the left are example trajectory predictions with the highest scoring predictions shown in green pointing towards the yellow waypoint. On the right is an example path of 8 waypoints traversed. We also evaluated our goal condition model on an underwater vehicle in the open ocean. However, in this case, the initial navigation policy was trained via imitation learning with the objective to collect interesting coral reef data. Our goal-dependent policy manages to trade off efficiency of reaching the goal for the opportunity to increase interestingness in the collected data. Overall, our robot autonomously executed 4 different 10-waypoint trajectories collectively spanning over 1 kilometer. It successfully reached 80% of the waypoints, some of which were behind coral reef obstacles. In conclusion, I've described a self-supervised approach for learning goal-conditioned navigation policies in unstructured and natural environments, and examined its application in both off-road driving on rugged terrain and in demanding underwater environments where the presence of surge, weather variations, and poor lighting conditions cannot be overstated. Thank you.